So last time we finished the control of power flow topic, I would say, for the most part. We discussed the various methods of controlling power flow, and we drew the phasor diagram for a synchronous machine connected to an infinite bus. We also drew, on that phasor diagram, we looked at the effect of leading and lagging power factor on the internal back EMF voltage or the generator internal voltage, which is EG here. This is magnitude EG angle delta. So delta would be is the generator's power angle, and EG is the generator's internally or back EMF or armature voltage, and VT is the terminal voltage, which we took typically as a reference in the last class. So we started with VT here, and we know that if we have a lagging power factor, then the current lags the voltage, and we drew the corresponding voltage drop across this reactance, and we drew the internal voltage EG corresponding to that, and we said that this line here, or yeah, the distance between this line and this line is proportional to real power, so we call this a constant power line, right? So we call this a constant real power, the constant real power line or locus, right? So if the voltage drop across, this is the I, this is my I, my current, I armature current, this is my armature current times the XL here times XL. This was this I times XL. This was my power factor angle. We said that this angle here is also the power factor angle. It's since this there's a this and this are separated by theta, and then I turned these together 90 degrees, which means that because I know that this current or this voltage drop across the reactance is 90 degrees with respect to the current, so turning these two by 90 degrees is like having this VT fall on this dotted line and this and then this IA over here. So the angle was here theta, and we said that this means that this is proportional to the real power, right? And we sort of moved. I said, okay, in another condition, let's say I have a voltage drop that is up here. What does it mean? It means that the current, that's the current, the armature current changed a little bit, so the power factor angle changed. So I would expect maybe the power factor angle to be like this. For example, this is the second case with the second voltage drop. This is still 90 degrees from it and added to the terminal voltage here. But I mean, again, maybe I drew it longer. I shouldn't have drawn it longer, but the idea is this is still falling. The new E for this case is also here, right? E is sum of VT and the voltage drop. E is sum of VT and the voltage drop. So this will be my new E for this case. Again, if you draw them with a ruler and stuff, it will be, of course you will see the angles. So this was an old delta between the two black lines, and this is my new angle delta. So this was delta old, and this is delta prime for the new condition. Both these conditions are delivering the same real power. Since E is falling on the same locus, then both of these conditions are delivering the same real power, but the power factor, the reactive power changed, and it's clear because we have a new theta here, right? So the power factor angle changed. This is theta prime for the new condition. Okay, so I fixed real power and I changed reactive power in this way. I can also fix reactive power. If I'm going to fix reactive power, then this angle is constant. This theta angle is constant, right? And let's work on the old condition. Then if I fix reactive power, then this is my first condition that I drew up, and then fine, I fix reactive power, then theta doesn't change, but the magnitude of the current changed, meaning that this black arrow will change in magnitude, right? So I fixed reactive power. I didn't change the angle, but real power changed with this new condition, right? So my new E is now here for this third condition that we drew, where I fixed reactive power, but I changed real power. Or I can fix real power and change reactive power like we did before, right? So this is a simple phasor diagram for the synchronous machine, and we talked about the limits of generator operation last time. We said that there's a limit on the armature current, right? There's a limit on how much current you can push to the machine, and it's basically due to the heat that the machine is able to dissipate. So this limit causes sort of a envelope here that you cannot exceed, because this here is this is the center of this circle here, and the center of this, the radius of this circle is proportional to the magnitude of the current, because the magnitude of this voltage drop is I armature current times the reactance. So this circle here has a center, and there's a limit to the radius that this circle can be drawn to, and that the limit is the heat that the machine can dissipate in the armature. The same thing with the field winding. The field winding is nothing but the rotor of the machine with windings wound around it to change the electromagnetic field, right? So this current as well has a limit, because otherwise you'll have too much heat, you'll melt the insulation, right? So this limit as well is what controls the magnetic field, which is what controls the magnitude of the back EMF voltage, right? So this magnitude of back EMF voltage, which has a locus here and a radius somewhere, depending on its let's say its maximum value is this value of E here, then this also has a larger sort of radius, right? It's a bigger circle with a different center, right? So this is one circle has a center here, so it's this sort of circle, right? And then one circle has a center here. It's a very different circle, right? And they both intersect. So the generator cannot operate outside this small circle because of the armature current limitations. It cannot operate outside this large circle because of the field current limitation. So that means the generator has to operate within both circles, right? So within this circle, and then within this circle. Okay? That's sort of the generator operating limit, if you would say. And of course, these are currents and voltages. You can go and translate. I mean, these are, I have voltage and I have values of current. I can take the specific value of, back EMF voltage and specific value of current that I have at every point around this area and convert it to a active and reactive power limitation curve. I'm not going to draw that, but on the file that I showed you last time for the UPS that talks about the leading power factor, it draws takes this and then draws a corresponding real and reactive power curve, capability curve of the generator. Right here, I'm drawing a voltage current capability curve. You can take all your voltages and currents and angles and translate that to real and reactive powers, and you will get, with the generator, when you buy the generator, you will get a capability curve based on limits and really reactive power, and it will be a curve that is based on what you've drawn here, right? It will look very weird. It's not going to be a circle. It will be something like this, like this, like this, right? It's a capability curve. It's a limit to within which this generator can operate. Okay, so please look up that file, and in that file you will see the corresponding curve on the real and reactive power axis. Okay, I'm not asking you to derive that curve. Okay, it comes from the limits on current and voltage. Okay, that's what we need. And we talked about the idea of limiting the leading power factor. So typically, the way we drew the phasor diagram now, we drew VT here. This was my terminal voltage, internal back EMF, magnitude EG, angle delta, and this was my VT terminal voltage here. And what we did was I took this armature current, added the drop, and calculated E. Added the drop for any current and calculated my corresponding value of E and delta. This is for lagging power factor. If I have a leading power factor, we talked about that last time, So let's say if you have a leading power factor, what does this mean? That this theta is going to be moving, right? If this theta moves, right, that means this, and since we know that this is perpendicular, this voltage drop across the reactance is perpendicular to the current that produced it. So this current will also move which way? This way, right? If this is going to move, if this angle, if this current moves to here, then the line that's perpendicular to it from this point is going to move. So it's going to move this way, correct? So this is still lagging power factor. Lagging power factor, the characteristic that you will know or you will notice is E will be greater than Vt. Eg will always be greater than Vt in the lagging power factor case, right? And that's where the generator AVR does its function. The generator AVR is what controls, or the automatic voltage regulator of the generator. It's what controls the field current of the generator. So this I field is controlled by a power electronics circuit. This is controlled by a power electronics box, some MOSFET or rectifier circuit or whatever, right? So you have to produce a DC current. So if you have an AC source, you have to create an AC to DC converter, and this AC to DC converter will have to control this current that is flowing into the synchronous machine's winding. Yeah. So what does this do? It basically controls the value of the magnetic field. If you control the value of magnetic field, this magnetic field is cutting the stator turns and hence generating a voltage across the terminals of these turns. Right? So the higher the magnetic field, the more the generator voltage would be. Right? So you typically are controlling E by pumping current in to increase the value of E beyond V. Right? That's what you're typically doing. However, if I'm going to operate in leading power factor, what is the function of this thing anymore now? The function of this now is to actually decrease the value of E. Right? So you're trying to decrease the value of E in this case. At some point, you're basically going to decrease the, so at some point you're going to lose, you're going to have zero current. If you put current through this winding, any current you put through this winding will have a greater value for E than V, which is what we are operating at in lagging power factor, right? But then you start putting leading power factor, you will accept, the generator will accept to operate with some leading power factor, but at some point what will happen is this current will fall down to zero. The field current will fall down to zero. At some point it will fall down to zero. Fine, you can reduce the number of turns a little bit so that E is not as large, so you will require higher current to generate a certain E here, right? But at some point, any small amount of current will create a voltage E that is greater than V if you're operating in leading power factor. So if I operate in leading power factor, I want a much smaller E, right? This is a smaller E. More leading power factor, smaller E, right? More leading power factor, smaller E, right? At some point, you cannot decrease the value of E anymore using your controlled current. In that case, you will be turning off the AVR. If you turn off the voltage control circuit of the generator, you have no control anymore. If you have a leading power factor load, this leading power factor load is causing the voltage, the terminal voltage, to be high, and you are trying to make sure that you're not increasing that further or changing it further by controlling E. That's, adding capacitive load. What will the capacitive load here do? This will be a leading power factor, right? If I have a leading power factor, it's going to be pumping in reactive power. So it will be trying to pump in reactive power into my generator, causing the generator to operate in leading power factor mode. If I push too much reactive power into the generator, I will lose control, and I will at some point have to shut down IF. If I shut down my field current, it means I have no control over the generator's voltage, means I have no control over reactive power in the system. We said, when we looked at the generator, when we looked at the equations for power flow, we saw that the equations for power flow clearly show a direct relationship between reactive power. We looked at, rectangular form. Yeah. When we looked at the equations for power flow, we saw a relationship where a very strong relationship between reactive power right? We saw, assuming we have theta close to 0, right? Remember our flat start is V's are equal to 1, angles are equal to 0. So let's assume that the system is not very loaded. So thetas are almost 0 and V's are almost 1. In that case, what did we say? Sine theta is a 0. And we also said that resistors are 0 for a well-designed power system, which means that the susceptance component is also 0 because susceptance we saw was equal to R over R squared plus X squared, right? Right? You know, Y is equal to 1 over Z, 1 over R plus JX, and then we multiplied by R minus JX. We ended up with R over R squared plus X squared minus, I think, JX over R squared plus X squared. I think that's what the result would be. So this is my susceptance component of the admittance. If R is 0, that means G is 0. If G is 0, then this term goes away because G is 0, and also because sine theta 0, sine of 0 is 0. So this term goes away, but we're left with a relationship, a dependence of reactive power, or a relationship between reactive power and voltage happening. So there is a relationship between reactive power and voltage. This is not 0. This doesn't go away to 0, right? There is still a term here that links or shows the effect between reactive power and voltage. Since this is not 0. And if there is a relationship between reactive power and 0, and these capacitors are pumping reactive power into the system, what that will do is increase the voltage. If you increase the voltage, what happens? So if the reactive power increases, and angle is a constant, and impedance is a constant, then what's happening? Then the voltage is increasing, right? So you have voltage multiplied by angle and impedance. Angle and impedance are not changing, right? There are certain values, and reactive power is increasing, which means that the voltage is increasing. The voltage in the system is increasing because these capacitors are in the system. You are no longer able to control the voltage of the system because you've shut down your field current winding on the generator. What does that mean? That means your system is prone to over voltages happening without your control, right? So that's what happens in leading power factor. So it's not a matter of leading power factor. It's a matter of how much reactive power, right? So I can have a capacitor connected to a generator, but it's a small capacitance. It's not pumping too much reactive power into the system. It's okay because it's a small amount of reactive power being pumped into the system. The voltage will not change much according to the equation, right? They're proportional, or they're linearly proportional, right? So if this is small amount of reactive power, it's okay. So if leading power factor is not a matter of leading power factor, it's a matter of how much reactive power you are pumping when you are in the leading power factor configuration. Okay? And we talked a little bit about that last time, and we said that all these UPS systems, this is a problem that especially happens when you have backup generators feeding utilities or feeding systems that have lots of data centers that are full of computers and power electronics, which have these big capacitors in front of every single input of a power converter, especially when they are not operating at full load. Because again, if you've studied power electronics, we know that we select capacitors at the input of the power converter based on how much these capacitors are required to maintain the voltage into the power converter. So if these converters are not running at full load, that means I have excess capacitance. This excess capacitance is causing what? It's causing a leading power factor. And this leading power factor is what is going to harm the generator if I have too much capacitance, right? So anyway, we talked about this last time. So so that wraps up the power flow discussion here. Any questions on the power flow control, the phasor diagram? I have one more thing I want to mention about power flow before we move forward. So we saw here that there's a direct relationship between reactive power, reactive power and voltages, and active powers and angles, right? We derived that last time, and we looked at the differentials, the differential equations, and we saw the dependence of active power and angle, and reactive power and voltage. So if so, we said that dp's, the real power and angles, there was a relationship not equal to zero. Where, under which conditions? And the conditions of a system that is not stressed, so theta equal to 0, v equal to 1, and r equal to 0. So a well-defined transmission, a well-designed transmission system with a light loading. These are sort of the summary of these conditions. Thetas are close to 0, voltages are equal to 1, r's are equal to 0. In this case, we saw that the dependence of real power on angle exists. So angle changes affect real power changes. How about real power changes with voltage? We said that that was equal to 0, actually, right? Real power changes and voltage. Let's go back to the equations if you want. Here. Okay. Theta is 0, v equals 1, r equals 0. Angle, real power and angle. Theta equals 0, so this is 0, right? Sine 0 is 0. Cosine 0 is 1, so it exists. So this exists, and b does not equal 0. So r equals 0 means g equals 0, right? So g equals 0, so this goes away. Theta equals 0, so this goes away. So the dependence of real power on voltage in a well-designed, unstressed system is not very strong. I'm not saying it doesn't exist. I'm saying, if the system had R, there's no such thing as R equals 0, right? But there's R equals a small value. So if it's 0, then the dependence of real power on voltage is almost 0, right? dP by dV is almost 0. But dP by d theta is not. It exists. There's a strong coupling between them. How about dq by d theta? Dq by this is g is 0, so this is 0. Theta is sine theta is 0. Since theta is 0, then this goes away. So the reactive power and angle, the relationship between them is very weak. Reactive power and angle, the relationship between them is weak. So the changes in angles don't really affect changes in reactive power. So there's no slope to this. This differentiation has no slope. Changes in angle will not affect the changes in reactive power. Okay, so that's what this means physically. And here, g is 0, so this goes away, but cosine 0 exists, so changes in reactive power and are affected by changes in voltage, right? So that's what these conditions mean. There's a strong coupling between reactive power and voltage, and strong coupling between active power and angle, and a very weak coupling between active power and voltage and reactive power and angle. Weak coupling. If there is coupling, our assumption is an assumption, but there is coupling, but it's weak, right? So if I have a huge system, okay, and I want to get a rough estimate of loading of equipment and ratings of equipment, I can use this assumption to simplify my calculations. Then, because I've killed half the Jacobian matrix, right? These are the components of the Jacobian matrix, right? If I kill half of them, then I don't have to do all these calculations, right? And that's what's called the fast decoupled method. So let's go back to the Jacobian matrix and see where these. So if you look at the Jacobian matrix now, we see that we've eliminated what? We've eliminated the coupling between real powers and voltage. And we've eliminated the coupling between reactive power and angles. So these are all zeros, right? They don't exist. So I have to calculate half the Jacobian matrix, right? So you have a 20,000 bus system with 40,000 equations with a Jacobian matrix, it's big, huge site, right? So what I mean, if you eliminate, if you want just a rough estimate, this is a good way to start. A good way to start to calculate your first iteration, for example, right? So then, and this is what they do in what's called the fast decoupled method, and I just have one slide about it here, and the idea is what we just discussed, that I was eliminating, this is after the power flow stuff. So after power flow control, we'll look at this capacitance thing again, but after the power flow control, this fast decoupled method is where now I've eliminated, right? I've eliminated J2 and J3, these big J's, J2 and J3 blocks in the Jacobian matrix. I only have J1s which are the dependence of real power on angles, and the J4s, which are the dependence of reactive power on voltage. This is incorrect. J4, if you go back to J4, yeah, J4 is this one, reactive power on voltage, right? So this is another typo, sorry. Okay? But, it's clear? I mean, I'm not going to ask you to solve a fast decoupled method. I mean, if I do, it's easier. But basically, the idea is you've eliminated half the Jacobian. You just automatically fill this and this part of the Jacobian with zeros. You just don't have to do it. Okay? And it's a good for a first approximation. But that's all it is. I mean, I just wanted to mention it. Yeah. And the Power World has the capability to do it. And I just learned yesterday that the Professor Overby, the creator of Power World, is joining Texas A&M. So he was hired last month. He was given an offer and he accepted the offer last month in College Station, which is good. I mean, I'm sure he will come and visit and stuff like that. So he's the creator of Power World. His company is the one that markets Power World. So I just learned yesterday from the department head that he's joining Texas A&M, which is, I think, a good thing for us. So, any questions now on this stuff? You should have questions since Overby is joining Texas A&M. Khalas then. Okay, we discussed this. The phasor diagram. I think I've drawn phasor diagrams here. They just draw a phasor diagram with an added capacitance. So here, if you have a pure capacitance as the load, right, then the current is leading the terminal voltage by 90 degrees, right? And what they did here, they also considered resistance. I didn't consider resistance before. I just considered the reactant, the JX of the synchronous machine. So, the resistive voltage drop is in phase with the current, and the reactive voltage drop is 90 degrees out of phase from the current. So this is what we were drawing before. The component of the voltage drop that is perpendicular to the current, right? So they considered the resistance here. So I think this is too big. I mean, even if you consider it, it's going to be a much smaller value, right? The resistance of a machine will be a much smaller value. So this is a considerable change. They just want to amplify the effect that we talked about. The idea of when you have a leading power factor, the internal voltage or the back EMF voltage of the generator is much smaller than the terminal voltage. Right? We discussed that when we were drawing the phasor diagram. So, any questions on this? Okay. So the other ways of controlling the power flow is tap changing. We said we control power flow using either tap changing transformers, or phase angle changing transformers, or adding reactive power into the system, or by generator circuit control, generator reactive power or generator active power control. So these are the ways that you control power flow, right? So there has to be ways to model that. So we looked at generator AV voltage and angle control, and we've looked at transformers and how we put them into our models before, but we never looked at the off nominal tap transformer. We're always looking at either the ratio be 1-to-1 in per unit, or 1 with an angle on the other side if there's a phase shift transformer in place. And for me, this is what we need to cover in this course. But if you are interested, I mean, to read more about this topic, basically, instead of having a one-to-one transformer in the per unit system, when we were drawing our single phase equivalents in per unit, we had our transformer equivalent circuit looked like this, just a series impedance, right? So, or as a series impedance with 1 e to the j 30th on the high voltage side, right? E to the j 30 was always on the high voltage side. That's how that's what we studied. Fine. Instead of having 1 e to the j 30th, this can be 1 to 1.1 e to the j 30th. If there's a tap. Yes, sir.
When you change your tap, you don't change your base voltage and base power?
When you change your tap, you don't change your base voltage or base power. No. Base power never changes for the system. And the base voltage will not change. That's why we end up with a 1.1 here, or 1.2 or 1.3, right? So we will end up with something greater than the base that we originally had, yeah. Right? So that's really the effect. I'm not going to ask you to solve problems with off-nominal tap transformers and tap-changing transformers in the exam. I will not ask you to do that. It's just a topic that is something, I mean, you will be exposed to it. I mean, I just wanted to bring it up, yeah. But I'm not going to ask you to solve problems on it in an exam. And you have not been assigned homework problems on it. I mean, you submitted yesterday's homework. I don't think there was nothing, right? There was nothing there. What, you're laughing. That means you did not submit the homework. Anyway, we'll talk about that later. Okay, so this was the end of this chapter. Basically, this is the end of this chapter. I skipped quite a bit of content, but I think I covered the main stuff, yeah. So any questions on the power flow stuff? Power flow chapter? So if there are no questions, so we'll continue to the transmission line chapter. So the main idea behind the transmission line chapter is, okay, so all we need to be doing in this course is really figuring out how to solve our single phase equivalent circuit, right? Since the beginning of the chapter, so since the beginning of the class, all we've been doing is trying to build a single phase equivalent circuit of a power system and solve it. That has been the objective all along, yeah. And I did the power flow problem, the power flow chapter first, so that you get a feeling of the full system, or what a power system engineer does, before continuing again and going back into a specific component and feeling like you're not an engineer anymore, right? So when we go back to a specific component, where it's more like the transformer chapter, where okay, why is this useful? Why is this useful, right? But the objective of this chapter is to figure out how to calculate the parameters of the transmission line's equivalent circuit. So we said that I don't care, when we talked about chapter 6, I said I don't care too much about how I calculate these parameters. Here we will go in more detail and figure out. At the end of the day, if I'm just in the power flow chapter, if I was given my R, my JX, and my JB over 2, my JB over 2, right? I was given these parameters in the tables, and then I've just plugged them in, right? I built my admittance matrix. They were used to build the admittance matrix, right? As soon as I plug in and fill my admittance matrix, I don't care what this is, right? I'm done. I have a system, and I have a Y-bus matrix. And then I know how to solve my power flow. My power flow equations iteratively, so that's it. Here we're going to go back and, okay, calculate R, calculate JX, calculate B, so that you have a feeling of the effect of different parameters, like the distance between the conductors on a tower, or the size of a conductor, or you would have an idea of the effect of the electric field, for example, that is causing this the charging current. There's a term called line charging current. These line charging currents are basically the currents needed to charge these capacitors. These capacitors, they don't exist physically. It's not a physical capacitor. But it's basically due to the fact that you have a big potential difference between the transmission line and your ground potential. So you have two bodies, if you want to say, with different voltage across them, with a potential difference across them, with a dielectric medium between them, which is basically a capacitor in space, basically, right? But it's a capacitance. If it's a capacitance, it needs, a capacitance connected to a voltage source or a line or a conductor, that it will have to be charged, right? So there's a phenomenon called line charging currents. These line charging currents are really what is required to sort of charge these fictitious capacitors, or these capacitors that are created by the construction of the transmission line that we have in space. Okay, so this is a phenomenon that exists. So if I have too much capacitance in there, what will this do? If I have too much capacitance and I end up with a leading power factor, like what we just discussed, right? We have to actually counter that. Remember, we were talking about power factor correction. You typically had a circuit that is resistive and inductive, for example, and you wanted to improve the power factor, and you added the capacitor in parallel, right? To be able to supply the reactive power locally, so you reduce the reactive power requirement from the source. That's what we've been doing before. But now, if these line charging capacitances are large, you are making the generator at the utility see a sort of a leading power factor system. So sometimes you'd actually need to add inductors. So we never talked about adding inductors in the system, but one condition where you would need to add the inductors in the system, series or parallel, would be to counteract the effect of these line charging currents that are due to these capacitances that exist because of the construction of the transmission line. So you sometimes need to add inductors in a line, okay, because of these, to counter the effect of these capacitors. Okay. Okay, so we'll figure out how to calculate R, X, and B. This is the objective of this chapter: calculate R, X, and B. Of course, designing a transmission line is a big multidisciplinary project, and electrical engineers sometimes end up working, on designing transmission lines and being in charge of developing these transmission lines. But I would like to say that most of the work is actually mechanical and civil in this field. But even though a lot of the electrical engineers end up working in this area, the bulk of the work is maybe not very interesting to the electrical engineers, because a lot of the work is related to getting permits to build a transmission line, getting permits to clear land, getting permits to build roads, because these are transmission towers. These transmission towers and transmission lines, they need to be cleaned, they need to be maintained. If there's a failure, you need to be able to access them. They don't look nice. They will reduce the price of property, right? If you don't want to have one of these transmission lines in your backyard, right? They have an effect on health. At least people are trying to link that for ages and do studies on the effect of magnetic and electric fields due to transmission lines on humans. So transmission lines are a big thing that people like to talk about, and people have problems with. It's like wind turbines. They have a problem with wind turbines because they don't look nice. They kill birds, so all the environmentalists have issues with that. Same time, they will have issues with, if you have, we don't have a forest here, but if you have forest and you're putting transmission lines within forest, you have to cut down trees, because you cannot have trees that are intermingling in the transmission lines, bringing the cables together, causing short circuits if there's rain. So they don't look good, which is what we did in here in Qatar and Ras Abu Funtas, the power plant. If you've driven by Ras Abu Funtas power plant going to the airport, or going past the airport to Sea Line before, 10 years ago, there were huge towers, it's like a big spider web going out of Ras Abu Funtas. Does anybody remember seeing that? Or 10 years is too much? 10 years is too much. I came here about 9 years ago, and it was like a big web coming out of the Ras Abu Funtas power plant. Now, they moved all of that, and it's underground cables. But the cost, of course, is very different, right? You have to dig underground. You have to have cables with insulation, right? These overhead transmission towers, they are bare copper or bare conductors. They do not have insulation, so it's cheaper to build them. If you need to maintain them, they're exposed, right? They're up there hanging, they're exposed. Underground cables, somebody needs to build something, and they will bring a big excavator, and they will break the ground, they will break the cable, and we will have to fix the cable or change the cable. So it's a lot of work to maintain and build an underground cable system versus a transmission line, right? But for cities like Doha, it makes sense that everything is underground because of distance, the density of people in Doha. Texas, for example, no. Texas, everybody likes to live on 2 acres, right? Have their horse, their camel, their cow. They don't have camels, but they have their cows. So and it's long distances, right? So you don't see underground distribution very often in Texas. Yeah, it's mainly overhead. They put wooden poles, cheap wooden poles with transformers every now and then to step up the voltage and connect users, and that's it, right? That's typically the distribution system in Texas. Yeah. Here it's almost 100% underground cables. I mean, at least I mean not 100%, but very close to that. Yeah. Like even the 400 kilovolt network, there are 400 kilovolt cables underground in Qatar. Yeah. Okay, so we talked about resistance, capacitance, and inductance a little bit. Of course, the resistance of these transmission lines are due to the fact that they are made of electrically conducting materials, copper or aluminum, that have some resistivity. So that's where the resistance comes from. The inductance comes from the fact that any conductor with current around it will store a magnetic field around it, and this magnetic field is basically linking conductors. Flux linking conductors due to a current is basically what is called inductance. And we will calculate the inductances, and I think you've done this in 322 probably, right? You have 370. Yeah, you have two conductors, and you calculate the magnetic field around it. You calculate the inductance between them. So you've done this before. So it'll be a quick review, and that's exactly what we're going to do. And you've done the same thing in 370 for capacitances. You've had two plates, and you've calculated the capacitance between two plates. First, you calculated the electric field, right? And then you calculated the voltage difference due to the electric field, and then we know that C equals QV, right? So from the equation of capacitance, the relationship between capacitance and voltage, you were able to calculate the value of the capacitance from the electric field and voltage. And for inductance, it's the same thing. You instead of electric field, you were calculating magnetic field, and from magnetic field and current, you will be able to calculate the inductance here. So it's simple. You've taken it before. We will not get into special cases. So, for example, there is a special case. The cases we've talked about and the ones you've taken in 322 before is one solid conductor, right? So for solid conductors, you've calculated the magnetic field inside, magnetic field outside, and then corresponding inductance. And you've put two conductors, and you've calculated the inductance between them. And you've done the same thing for example, the electric field between 2 points, right? This is all we will do. That's what we will do in this chapter, but there are special cases. The special cases are, for example, in a power system, sometimes if you drive by a transmission line, you will see a tower with tower span and holding the three phases here. But if I zoom in here on this, I will see that this is not really composed of a single conductor. It's composed, for example, of a bundle of conductors with spacers between them, mechanical spacers between them, right? Sometimes you would see that. And these are all one phase. These are all this conductor that you have here. So phase A, for example. So, and we sometimes do this, and it's called a bundle. So this is a conductor. This is called the conductor bundle. We do this for many reasons. We do this we don't want to use one single big conductor because of the current carrying capacity. That's one. The other reason is these conductors have an electric field around them. The electric field from one conductor, if you remember from 322, and we will go through it again, the electric field around the conductor basically decreases with distance, right? So, but there's an electric field around the conductor, right? Emanating from the conductor. So the magnetic field is around, the electric field is perpendicular to the surface area of the conductor, right? So if I have one conductor here with an electric field emanating out, I have another conductor here with the electric field emanating out. In this zone here, they are actually opposing each other, and there will not be an increase in the electric field. The problem with an increase in the electric field is if you have air and let's say there's some water in the air or some fog, etc., etc. Then electric field, between, if you have an electric field in the atmosphere, that means any 2 points that are in this electric field have a voltage difference between them, right? If you have an electric field, any 2 points in space in this electric field will have a voltage difference between them. This voltage difference, if this electric field is high, can at some point break the medium between them. If this is air, then the breakdown voltage of air is 30 kilovolts per centimeter. How about if it's air with lots of fog and water, with lots of water, right? Then the breakdown voltage will decrease. Sorry, go ahead.
These four lines in the bundle are the same phase, right?
Yeah, same phase,
So
same phase.
there's no voltage difference between them.
There's no voltage difference between them, but there's an electric field due to each of these conductors. So every single conductor will have an electric field due to the current or the charge on top. Now, I'm not talking about the voltage difference between the conductors. I'm talking about you have a single conductor. This has charge Q on top of it. Will there be an electric field due to this charge Q or not? So there will be an electric field due to this charge Q. So this is the electric field I'm talking about. And I'm talking about the voltage difference between 2 points in space, not between the conductors. Right? So what will happen is these 2 points in space, because of the fact that they have an electric field, then what will happen is there will be a voltage difference. This voltage difference can break down this air or the medium between. And this is called corona. And corona is if you drive next to a transmission line, especially after rain, you will hear a hissing noise sometimes. And this hissing noise is basically this voltage or this electric field breaking down the air around the conductor. So to avoid that, you space conductors far from each other, or if the voltage is very high, if the operating voltage of the line is very high, then you bundle up the conductors to reduce the electric field around or in the vicinity of the bundle of conductors. Yeah, right. So it's corona. That effect is corona, and due to the force, you don't want. If you have a very large current, you still don't want to carry one single big conductor. You prefer to deal with smaller conductors. Just transporting one big conductor is very tough. So you will end up breaking up the conductor into 4, for example, or 2, or whatever, and transporting those is much easier. Stringing those is much easier, right? So we actually, these transmission lines, they are strung, so they, you hold them, they're held from one side, and you string them through the transmission towers. So you have one tower after one tower, one tower after one tower. Every couple of towers, what you do is actually you have one, somebody stand here or some people stand here, and you put the transmission line, like putting it through a needle. You're hanging it on top, you're hanging it on the insulator. So this tower will have a insulator stack, because this is high voltage. This conductor is at the high voltage, and this tower is typically going to be grounded. We'll talk about that. So then there will be a voltage difference between this conductor and the tower body. So you want to insulate with a insulator. So we have these insulators that look like, I have some pictures of them later, but stacks of insulators. They have irregular shapes, and these irregular shapes are made so that there is no easy path for, let's say there's dust deposited on top of these insulators, and water comes, and dust, and water, and dust, and water. Then you will create a conducting path from the tower body to the high voltage cable that you have, right? So high voltage transmission line. So the bodies or the design of these insulators are such that they make this path very difficult to create the short circuit, path for short circuit or an arc to occur. But you still have to clean these insulators. So you actually have to go in, and I have, for example, a monthly, Kahraman, for example, has a monthly report. This monthly report shows how many insulators they clean every month, and how much of the transmission line they clean every month, which means they have to access these transmission lines, right? So you cannot have these transmission towers in isolated places that you cannot access, right? So you have to have roads leading to the transmission, to each of these transmission towers. Yeah. So, and the way we hang it, so we string, it's called stringing an insulator through. So you actually string it through. You have these, you sort of hanging on like a pulley. You have a pulley hanging on the bottom of these insulators, I'm not good at drawing a pulley, but you have a pulley, and then you just string the cable through. Right? Just a pulley that you string the cable through between some towers, and then there are towers that allow you to just string it through, and these are called suspension towers. Suspension towers are towers that merely suspend the insulator. They don't add any mechanical stiffening capability to your transmission line's mechanical structure. And then there are towers called string towers. String towers are every few towers. You cannot just keep stringing the insulator between towers. At some point, you have to terminate because you have to put some mechanical strength. I mean, this transmission line is very long. You cannot just merely have it fixed at one point and fixed at another point. What if it breaks in the middle? If it breaks in the middle, it will fall. I mean, if it falls and it's connected to the generator side, it will cause harm, right? So what we want to do is every couple of towers, we actually terminate the cable so that the cable will come in. The cable will come into the tower, hang on. So this is a suspension tower where the cable was merely just hanging in there, hanging on the tower, right? And this is called a string tower. In a string tower, I actually terminate the cable. So I actually cut it here and mechanically fix it to an insulator here. And then what I do is I have an insulator, an outgoing insulator, and I sort of connect these two together. Right? So there's a big difference between these kinds of towers. This is called a string no, this is a suspension tower. Suspension tower, and it's called a string tower. So they're every couple of suspension towers. If you drive by, going to Ras Laffan or something, and drive by, a set of series towers, right? You will see that most of the towers will be this type. Most of the towers will be this type because it's cheap, right? I don't have to terminate. I just string it through like a needle, like a thread and a needle. You just string through a couple of towers after each other. But then I want to make sure that every few points I have somebody holding the line, right? Something has to hold the line. I don't want the line to just be connected from one point and connected from the other point, and that's it. I have to have some strength added to this line every few towers, and that is called the string tower. And then physically what happens is the cable comes in, transmission line comes in, terminate, and then outgoing, terminated as well, and then there's just a connection between, the electrical connection between. I'll show you some pictures of those. Last year I gave bonus points for people who gave me pictures of the two types of towers in Qatar. So if you want half a bonus point, give me a picture of, and with the GPS location in Qatar, because you may get it off the web. Yeah. But if you get me pictures of two towers, one suspension and one string, these two types of towers, you get half a bonus point. Yeah. So Mariam is not here, but I know she will still do it. Yeah. So anyway, so let's go through the slides. So as I was saying, underground transmission in the U.S. accounts only for 1% of the total transmission, right? This percentage is much different here in Qatar, because of the size of the country. And again, these transmission lines are operating at all voltage levels. It's a spectrum of voltage levels. Guys, if you have questions, you can ask me. Hello? Yes? Ask. If you have questions, ask. So these transmission towers come in many different sizes and configurations, and it's mainly because of their ability to insulate the voltage. So you have voltages all the way from 2.4 kilovolts that are you have smaller distribution towers. Again, in Qatar we don't have distribution towers at all. I don't think there are any distribution towers. There are transmission towers, of course, but not distribution towers yet. In the U.S., it's very common to have distribution towers. It's just a smaller tower. I mean, for lower voltages. I mean, distribution level voltages are voltages, let's say, up to 15 kilovolts.
It's on wood.
In the US, a lot of it is wood. Yes, a lot of it is wood towers, as you see here. I have a picture. So this is typical distribution tower. Short wood. It's this is typically what it is. But again, here in Qatar, we don't have any of those. Yeah. So we go all the way from distribution level all the way to high voltage DC lines. And again, the power engineers sort of agreed on some names, right? So the lowest level voltages would be the distribution towers or distribution voltages, yeah. And then it's the subtransmission. Subtransmission is fine, higher than the distribution, and it's not transmission level, so it's they called it subtransmission. So typically the 46 to 69 kilovolts. In Qatar, I think subtransmission kilovolts are 33 and 66 kilovolts. So the substation, for example, that is the big transformer that's behind city center, is fed with 66 kilovolts. So that's sort of the subtransmission voltage here. Then the high voltage lines are in Qatar, they're typically 132 and 200 kilovolts. So Ras Gas, for example, is fed by a Kahrama connection of 132 kilovolts. Kahrama has a network of 200 kilovolts, so we don't have 230. So the numbers in different countries differ, right? And then extra high voltage lines, Qatar has a 400 kilovolt network. They don't have 345 or 500. So the higher the amount of power you need to send, of course, the higher the voltage you would like to push, right? So it's typically in U.S., China, Russia, places where you have very long distances and huge amount of powers, then you would need to ramp up the voltages. So you also have, of course, DC lines. So DC lines actually right now, I think Siemens just said that they're able to produce a 1.1 megavolt DC line. And 1.1 megavolt protections, breakers, and equipment to go along with that DC line. So this is a bit outdated, the numbers here. But the idea is, of course, the more power. And again, high voltage DC lines are typically used when you need to link or transmit bulk power, huge amounts of power between 2 points. And because we have power electronics today, you can do that using high voltage DC. Take this DC and then convert it to AC afterwards. And we studied in 438 the topologies that are typically used in high voltage DC lines. Again, towers. These towers would have the phase conductors, as we talked about. These would be the three-phase conductors. And then these phase conductors are hanging by insulators. So these are insulators. I have better pictures of those later. But they basically insulate the high voltage lines or the live lines from the tower body. Why? Because the tower body is typically connected to ground. And the way this grounding thing is a big deal, actually. You actually design the grounding system. It's not a matter of just taking a piece of wire and connecting it to the ground, right? So you design a ground mat, for example. You design a mat or a metal web under the ground, and you would have to make sure that it's wet. The area is wet or a bit humid, so that the electrically the connection between the mat and the ground is very well defined. And this mat, sometimes you would have grounding rods placed around the mat as well to even further strengthen that connection. So there's a ground rod here. If you go out from the Batil cafeteria downstairs, if you go out from the Batil cafeteria downstairs out into the parking lot, you will see there's like a small manhole cover, and it says ground rod. So it's a small rectangular ground rod cover. I don't think you can open it, but it's to basically be a copper ground rod connected to ground, and connected to so there's a substation, there's a transformer, right next to on the right. When you're walking out into the parking lot, there's a big transformer on the right that feeds the building. Inside the building, it's covered, of course, you cannot see it, but there's an electrical room, on your right when you go out. So it's probably going to be that ground rod is connected to the ground system, the ground of that transformer. Yeah. So anyway, okay, tower hold insulating, foundation and grounding. Of course, foundation is the civil foundation to keep the structure up, and the grounding is more of an electrical design criteria. There's books on grounding. How do you design grounding systems? You want to make sure that the grounding system, of course, again, if current is flowing, you want to make sure that if somebody is standing on the ground, right, that between their legs, for example, there's no big voltage difference. Otherwise, you will burn the person, right? So if there's a lightning strike, for example, and the current from the lightning strike is flowing from the shield conductor. These shield conductors are typically used on top of these towers, that they can be an easy target for the lightning, right? So they will be easy target for the lightning to hit, and these shield conductors will be connected to the tower's ground. So they will pass the lightning currents all the way to ground. So if you have these huge currents, and you have a ground mat, for example, or a grounding system, and somebody's walking, current flowing. I mean, if this lightning current is going to flow into the ground, and if somebody's standing here, you want to make sure that this grounding system, actually the resistance, the voltage difference between 2 points on the ground is not very high. Otherwise, you can kill a human, right? Humans would die, for example, I think 50 milliamps. If there are 50 milliamps of current flows, you die or something, or 1 million. I think it's 50 milliamps will kill you. 1 milliamps, 2 milliamps will tickle you, but 50 will definitely kill you. So, and I think the resistance between from fingers to fingers, the resistance of a human, I think, is about a kilo ohm. So I don't think you want to try it, but if you put a few thousand volts, between your two hands, I'm sure you will injure yourself seriously. So, but again, there are calculations. So, and it's when you design a grounding system, you actually look a lot about at these things, and you want to make sure that any 2 points on the ground don't have a big resistance between them. So that's why you would, for example, put a big grounding mat. For example, you won't put a single conductor. You put a single conductor connected to ground, and somebody's standing between 2 points on this conductor, on top of this conductor, then there's a voltage difference, and this person will definitely die. So we don't talk about grounding system and grounding system design in this course, but it's a consideration to look at, yeah. And then, of course, there are shield conductors. We said they're typically put on top here to guide the lightning. And then sometimes there's also fiber optic conductors. So these shield conductors sometimes will also have along with them some fiber optic cables. So yeah, when we talk about power systems protection, we will see that in many cases we have to communicate between different points in the power system, because we want to make sure that the current we measured here and the phase angle versus the current we measure here, the phase angle, are the same. Otherwise, we have a problem in the middle, right? So there's a lot of fiber optic communication happening, fiber optic and microwave communication in the power system. There's a lot of that going on, yeah. So these are the main components of a power system, a power system tower, yeah. Again, these towers come in many shapes and forms. You can take a course on tower design. We won't spend too much time on that. The idea is there are two main types. This is a string tower. So this is a kind of tower that will add mechanical strength to the lines, right? The line comes in, is terminated here, and then outgoing is terminated as well, and then there's a connection between them, right? So if one side falls, for example, it will not affect everything else on the other side, right? So every few suspension towers, you have to add one of these kinds of towers, especially at high voltages. This is a guide lattice tower. Guide versus just a simple lattice. Simple lattice tower can stand without, with conductors in different configurations, and does not depend on the weight distribution of the conductors for stability too much. It does not depend on that highly. These guide lattice towers are very different. You sort of need to make sure that the cables or the transmission lines balance the weight of the tower so that it doesn't fall over or it doesn't break. You don't add too much mechanical forces to bend the tower. So it's designed so that you distribute the transmission lines in a certain way, and they have to be a certain way for it to be able to stand up and maintain its mechanical strength. Yeah. But this is also, I would say, I think this is, I don't know, it's not very clear, but this is suspension of strain tower. Yeah. Go ahead, sorry. Go ahead.
Yeah. Why does in the previous picture, why does the line split into three? If you look at the far left.
Far left here?
Yeah, at the line split into three.
2 or 3? 2, 2, and 2, right?
No,
Where
further
3?
down the line.
Further down the line. Where?
No,
Here?
at the tower, at the first tower, the line's split.
No, this is probably the insular, and that's what I was trying to say. If this, I was trying to see if this is a string or strain type tower, but I think these are insulated, but they didn't. This is not a good picture. I think it was a good picture for a guide lattice tower, or a picture just to show that this is a guide lattice tower, meaning these types of towers, they sort of require the cables to be, or the transmission lines to be put in a certain way so that the tower doesn't fall over or twist. So this is not a good picture for. I'll try to see if I have a better picture. So this is a picture for not suspension, something similar to a suspension tower, where I'm not, again, this cable is one continuous cable, right? This transmission line or cable is going through continuously. It's just held on top of the tower. In this case, it's just held on top of the tower, right? There's no termination and connection between them. So it does not add mechanical strength to the system yet. Yeah, I don't have too many good pictures, but I mean, again, that's why you can. The bonus assignment is good. Then you'll go around Doha and get some good pictures. Yeah. Okay, so we have a few more, some more time. The best, of course, again in the equivalent circuit of the transmission line, we had the series resistance and inductance. Of course, we want to reduce the resistance as much as possible, and the best electrically conducting material for us to use would theoretically be copper. Copper has a high current carrying capacity and very low resistivity, right? So ideally, everybody would be using copper for these overhead lines. But of course, copper is very expensive and it does not have. Copper also has good mechanical strength, right? So, but not as good as aluminum. So copper is great because of the electrical conductivity parameters, but it's also very expensive and it's not readily available as like aluminum, right? So aluminum is much cheaper, much more readily available, has decent mechanical strength, right? So not as good as copper. Aluminum is okay. So aluminum seems to be okay. Aluminum has higher or lower resistivity than copper. The resistance of an aluminum and a copper conductor, same diameters, which has higher resistance? Aluminum. Aluminum has higher resistance, right? So aluminum has higher resistance than copper, but it's cheaper, right? It's readily available. Strength-wise, copper is stronger than aluminum, so aluminum has some disadvantages, right? So it's cheaper, readily available, but has some disadvantages of resistivity and mechanical strength, right? So what do? What we do in transmission lines is we use what is called ACSR. So it's an aluminum conductor, steel reinforced, right? So this is the workhorse of the transmission line industry. It's an aluminum. It's an aluminum conductor with a steel core. So they put steel in the steel as a core, so that you get the mechanical strength that you require. And then you put aluminum conductors around it. You typically have small strands of aluminum conductor that you place around the steel core. And you sort of twist around the steel core, right? So I have a picture of that later. So any questions on that? So this is the workhorse. This is what people use. I mean, single copper conductor is typically not used at all. It's very expensive, and it's not something that people utilize. So workhorse is ACSR. Of course, there is more technologies, right? So people try to come up with, people, if you Google search, and you will see people trying to talk about superconducting transmission lines. So superconducting transmission lines are, great concept, right? The idea would be make R equal 0, right? This is the ideal case of R equals 0. Why do people want to worry about that? Because really, if you Google search as well and look at the efficiency of transmitting power or from the generator all the way to the consumer, the efficiency of this is very low. So the efficiency of this delivery of from the fuel all the way to the consumer, the efficiency is like 35%, right? So efficiencies of electrical power generation, all the way from fuels all the way to the consumer, almost 35%. So it's a very poor efficiency, and a big bulk of that is in the transmission, is losses in the transmission and distribution, of course. So if we're able to make cables that are superconducting, resistance equals 0, that's great, right? So there are people that have develop transmission line, superconducting transmission line. But of course, it's very expensive, right? Superconducting materials need to be maintained in a certain nitrogen environment. I mean, which is expensive to be able to build an infrastructure like that. Yeah, but they are utilized in applications like these electron colliders and stuff like that. People in that area are very big on these superconducting materials. Yeah. Transmission lines, ACSR. So, and because these transmission lines are typically so as I said, they're typically aluminum strands around the steel core, right? So the definition of, the calculation of the electric field, the magnetic field that we will talk about is based on, having a single conductor. And then, of course, we can get into the details of how the effect of stranding on the calculation of electric field and magnetic field. We won't get into that. I think we will do the basic calculations so you get an idea of R, L, and C, how to calculate them. And then the idea of calculating R, L, and C for a bundled conductor system, I will ignore that. Right? I will just do one type of simple calculation to give you a feel of it. Why? Because this is actually done today using software. A lot of this stuff. So you would actually there are softwares that you plug in the type of cables that you will use and the distance between the cables, and they will tell you what the corresponding parameters R, L, and C are that you will use in the equivalent circuit. Right? So, but it's good to have an idea where that's coming from, which is what we'll do in the class. Okay, so this is called, so they typically give these conductors names. So this is called 54-7 cardinal. So the appendix A3 in the back of your textbook, and we will look at an example next time, where they give them names, and these numbers here stand for the number of aluminum conductors or aluminum strands, and the second number stands for the number of steel strands. So this is 54-7. It has 54 aluminum conductors and then 7 steel conductors, 54-7. But this is 37 here. It's again, the steel is for the mechanical strength. Any questions on this? So we will stop here. And this is just another slide on different types of conductors. So basically, what they try to do is improve resistivity by adding alloys, and improve mechanical strength by adding alloys as well, right? So that way they can reduce the amount of steel in the conductor. If they reduce the amount of steel, then the weight of this conductor will be decreased. We stop here. Next time we continue, inshallah.